Okay, moving to the another part, that is example number 1.15 of chapter number 1. Our consideration over here is electric field, which is given as a 3 cross 10 to the power 3. Look over here, there would be a I cap of Newton per Coulomb. And what is the flux of this field through the square of 10 centimeter on the side whose plane is parallel to the y and z plane? If we are drawing this figure, then it will be quite clear for us to find it out flux for it. Let's say this is the area, which is x. It is the direction of electric field because it is mentioned as I cap. I can mention as a E of x, and our plane, which is in the y and z direction. So this is a y and this is the z, the direction of this plane, which is also parallel to it. So we can just say that flux phi is either there would be the indefinite area, we can say that it would be the integration, but for the definite area I'm just opening this bracket, that is called as EA cos theta. But here our theta would be 0, so I can have flux phi of the area because L square is called as the area, our length is called as a 10 centimeter, so our flux phi for the electric field 3 cross 10 to the power 3 and area is called as a 0.1 square. So flux phi we will have is a 3 cross 10 to the power, that is 0.1, 1 by 10, 1 by 10, so that is called as a 30 Newton per Coulomb. Second part, if the phi EA cos theta, but our theta is mentioned as a 60 degrees, so we can have a, this is 30 Newton per Coulomb. So we can have E A cos 60 is 1 by 2, so we can have a 30 by 2, and that would be 15 Newton per Coulomb. So this is the direction and the electric field of x and y and z, where our plane is located into the y and z plane. And whenever such type of examples are there, so I can just say that always think if your plane is in the y and z direction. So prove or find it out example for the electric field if there would be in the y and x plane. Moving to the example number 1.16, where we have been given that what is the net flux of the uniform electric field, which is having the relationship with the previous example 1.15. It means that our data of electric field, our area of the square is the same as the previous one, but the only condition is that our net flux, it is uniform electric field, which is as per I have told you that 3 cross 10 to the power 3 I cap, and our cube, which is having the side 20 centimeter, it means it is cuboid, and we have to find it out surface is parallel to the coordinate of the planes. If we are seeing such type of example, so we have a such a cuboid which is holding the sides 20 centimeter and electric field. If you see that previous example, it is like giving us the reminder of a thumb rule, because our x and y plane over here and here, and our thumb is giving us the direction of electric field. But in this example we have a cuboid which is making an angle of theta equals to 90 degrees. If you see the previous formulas, it is giving us that idea that whenever our theta equals to 90, our flux will be 0 because cos 90 is making an angle value 0. So our net flux of this coordinate of the plane, that is giving us the value 0. Next example, which is another good example, which is giving us the previous theoretical concept. The careful measurement of electric field at the surface of a black box indicates that the net outward flux through the surface of the box is if you see that flux phi is given, it is called as 8 cross 10 to the power 3 Newton meter square upon Coulomb. That is the unit of a flux phi, because if you see that flux phi having the unit q by epsilon 0 or q by epsilon 0, so flux phi is equals to 8 cross 10 to the power 3 Newton per Coulomb into meter square, and which is called as The same type of example, moving towards find out the net charge inside the box. In the class we have discussed whenever we have a cube and in this cube our charge is aligned, so we can have a flux of phi q by epsilon 0. It is having 6 sides, so multiply by 6 for the each corner. So this is formula of edge, q by 8 epsilon 0. But our bingo is that you can remember this formula by q n number of epsilon 0 sides. So our formula, we can find it out with the help of n into E is equals to q. So our n is equals to q into E is equals to our flux of phi q by epsilon 0. So we can have q is equals to flux of phi into epsilon 0. Our value of phi is 8 cross 10 to the power 3 and the value of epsilon 0 is standard value 8.85 cross 10 to the power minus 12. So I'm placing these values over here, which is 8 cross 10 to the power 3, 8.854 10 to the power minus 12, which is giving us the value 0.007 10 to the power minus 6 coulombs. Second question, net outward flux through the surface of the box will be 0. Can you conclude that? Why? Whenever our flux of phi is 0, there are only two possibilities. Either your angle would be 90 degree or either your net charge would be 0. Then and then you can say that our flux will be 0. So for the second question, they have asked us why our flux will be 0. There are two possibilities. Either there would be a no charge or maybe the angle made by electric field and the surface area would be 90 degrees. A 1.18 example is somehow tricky example. Why I'm using this word tricky? Because it is not giving us the direct figure, and the thing they want to find us the values. These values are not direct. In the figure you can see that there is a point charge which is 5 centimeter above the surface of the square of area 10 centimeter and 10 centimeter, and we have to find it out. Show that what is the magnitude of electric flux. In such type of figure, first of all, whatever data has been given to you, collect that properly. I'm drawing a cuboid, and from the top view its a distance is called as a 5 centimeter, and over here you have a one charge. Okay, so a point charge plus 10 microcoulomb, it is at a distance of a 5 centimeter above the cuboid, and its a center would be there. This is a cuboid. From the top view, if you view it, it is giving us a such type of figure. That is why I'm using this word trick. In the hint, think of the square as one of the face of a cube of the edge 10 centimeter. Sorry. So I have to find it out. It's a charge. So my Q is equals to 10 microcoulomb. So I can have a 10 cross 10 to the power minus 6 coulombs. So 10 to the power minus 5 coulomb is my value of Q. I have to find it out a flux. So I can have Q by 6 epsilon 0 5. As I have already discussed over here, for the corners there are 8 corners of the cube, that is why Q by 8 epsilon 0, and there are 6 sides or edges, that is why Q by 6 epsilon 0. So I have this value 10 to the power minus 5 divided by 6, 8.85, 10 to the power minus 12, and this is giving me the value of 5. So you can see that a very simple example, but it is having such type of arrangement which is giving you some of the goosebumps. 1.19. This is the example which has been asked for the MCQs. A point charge, I can use Q equals to 2 microcoulomb 2 cross 10 to the power minus 6 coulombs. A surface which is having 9 centimeter on the edge. Apart with that, we have to find it out. Flux would be what? Okay, flux of phi equals to Q by epsilon 0. Our charge is on this surface, that is why we have, let's say, cuboid charge on the surface. That is what, so flux will be outside. Q by epsilon 0, value of Q 10 to the power minus 6, value of epsilon 0, it is 8.85, 10 to the power minus 12 is going in numerator, giving us a plus. We will have a 2.26 cross 10 to the power 6 Newton upon Coulomb, that is called as a meter square. Next example, that is called as a 1.20. A point charge causes the electric flux. So we can have a flux. See, this is the only example in our exercise which is giving us the value negative. It means it is only because of the negative charge. And our radius, Gaussian surface having the radius, that is called as R. I am using this word 0.1 meter. We can say that if it is giving us a such type of thing, we have to find it out. It's a charge. Very first question, if the radius of the Gaussian surface would be doubled, so we can write it down that a Gaussian surface doesn't depend on its radius. So there is no question, it is directly bifurcate, and directly you can boycott such type of question. If radius is double or triple, there is no effect of a Gaussian surface, because the Gaussian surface does not depend or having relationship on the radius. Second part, what is the value of the point charge? We have to find it out, the value of a charges. So yes, we have value Q by epsilon 0. We want to find it out. Q is equals to epsilon 0 into 5. So we have a epsilon 0, it is 8.85, 10 to the power minus 12, and flux phi is minus 1, 10 to the power 3. So I can have a minus 8.85, 10 to the power minus 9 coulombs. So as I have mentioned you, whenever we were reading this term, if your electric field is negative, electric flux is negative, so obvious there are possibility your charge might be negative. Now moving to the example number 1.21. 1.21 is, again I am using this word, it is called as a game of words. Why I am using this word game of words? Because if you read, they have given you two type of distances, one in terms of radius and another in terms of a distance. A conducting sphere, yes. Example number 1, it is giving us a reminder. Yes, you have a charge, they are very much minor in nature and having the droplet type of geometry. So it is a sphere which is having the radius, so it's a radius R equals to, let's say I am using this word 0.1 meter, and from that its edge, one point, let's say I am just putting that point A, so from that to 0.2 meters. So from the center of the sphere, our electric field E is equals to 1.5 cross 10 to the power 3 Newton per Coulomb. This distance is a 20 centimeter, it means that 0.2 meters, and this radius is called as a 10 centimeter, means it is called as a 0.1 meter. We have to find it out, it's a charge value. Okay, electric field is given, so we can use that kq by r square, but confusion over here that which one we have to take. Always your sphere of radius might be of any radius, any distance, or any diameter. Its charges are always located on its surfaces. That is why we will consider the distance or r as only the distance from its edge to that given point. So we can have r dash, which is I'm using that 0.2 meters only. So this is the distance, and this is the word I have used. It is called as a game of words. We want to use that charge E r dash is square divided by k. So q is equals to electric field 1.5 10 to the 3.2 square divided by k, that is 9 cross 10 to the power 9. So our value of a charge q would be minus 6.67, or you can say that that is called as a 6.67 cross 10 to the power minus 9 coulombs. Example number 22. You have been given that a uniformly charged conducting sphere, as for the previous one it is also conducting sphere, their radius would be 10 centimeter, but here we have a diameter that is called as a d 2.4 meter, only with the thing required is called as a radius is called as a 1.2 meters. It's a surface charge density, yes, it is called as a sigma. We have discussed about it. It is called as a 80 microcoulomb per meter square. Look at the unit, it is called as a coulomb per meter square. So 80 micro 10 to the power minus 6 coulomb per meter square. It is giving us a value of a sigma. We have to find it out. It's a charge on the sphere, and we can find it out. It's a flux. Yes, very first part, A part, sigma is equals to q by a. So q is equals to sigma into a, where area is called as a 4 pi r square. So my q is equals to sigma, which is 80 10 to the power minus 6 4 3.14. Your radius is a 1.2, it's a square. Though we have a 10 to the power minus 6, so our answer would be in the terms of 10 to the power minus 3 into, that is 1.4 coulombs. Flux phi, q by epsilon 0. Value of q, that is we have found it out, 1.4 cross 10 to the power minus 3, and epsilon 0 8.85 10 to the power minus 12 going in numerator, that would be giving us a plus answer. So find it out. It is in the terms of Newton per coulomb meter square. Another example, that is called as a 22nd, we have discussed already. So 23rd one, the infinite line charge produces the electric field that is called as a 9 cross 10 to the power 4 Newton per coulomb, and it is called as a, we have to find it out, so electric field for the line distribution. If you remember those formulas, so we have discussed about that electric field for the conducting wire, or you can say that for the finite length wire. So again, looking at this formula, for the finite length wire, our electric field is called as a 2k lambda by r. We have modified it in the terms of lambda 2 pi epsilon 0 by r. So again, if you look at this term, it is giving us that an infinite length line charge produces the electric field value E is equals to 9 cross 10 to the power Newton per coulomb, and our distance, it is called as a length, 2 centimeter 0.02 meters. We have to find it out. Lambda linear charge density. So our formula of E is equals to 2k lambda by r. Double implies ER by 2k is called as a lambda. Thus we have the value of electric field 9 cross 10 to the power 4. Our distance is 0.02 meter. Our 2 is okay. K is standard value, 10 cross 9 cross 10 to the power 9. So lambda would be something like 10 to the power minus 7 coulomb per meter. So this is how you can just solve such type of examples. Last example of this chapter, that is called as a two large metal thin plates which are parallel to the close and each other. You can say separated by some distances where their values of a charges are 17 cross 10 to the power minus 22 coulomb per meter square. Where another thing which is also holding the same charge density, but its charge value would be negative compared to the previous one. So first of all, I am drawing these two parallel surfaces. One that is called a surface A, second surface B. For our simplification, I am in the classroom, I am also discussing that always take that it is a central part or mid part. Right hand side is positive, so you can say that positive EA. Left hand side is a negative EA. Here negative EB. Here that is called as a positive EB. So you can have a three parts. This is region 1, this is region 2, and this is region 3. Whenever such type of surfaces, consider that is a paper, and in between you are putting a ball which is having some charges, so it is holding two surfaces, one bulgy side on the right hand side, one bulgy side on the left hand side. So we can have a E of A is equals to sigma by 2 epsilon 0, and E of B is again sigma by 2 epsilon 0. For the surface 1, if we will add EA plus EB, but you can say that EA is positive and EB is negative, thus our net electric field will be 0. Second part, at a midpoint part, we can have a EA plus EB. So we can have a sigma by twice epsilon 0 plus sigma by twice epsilon 0. So we can have a sigma by epsilon 0. You can place those values. Again, right hand side, EA, EB. EA is positive and again EB is also positive. But EA is positive, it means that its value is a sigma by 2 epsilon 0 plus minus a sigma by 2 epsilon 0. Why I am using such type of notation? Because they have mentioned that their surface charge densities are opposite signs. That is why plus is there, but EB contains negative polarity. So you can say that net electric field will be 0. If you remember this example as a theorem, you can say that electric field will be outside or either inside 0 whenever you have a system of a charges. So in this example, we have an electric field whenever we have a two charges, both are, one is positive, another is negative. If you say that left hand side, it is called as a minus EA, it is again minus EB. So minus EA minus and minus plus EB. So for your simplification, you can say that minus EA, and with sign I can just say that it is also 0. So this is the end of the chapter number 1's examples. Hope you may like it. You may find it out interesting, and revise these examples twice or thrice times, and you cannot forget such type of examples, because in this chapter you can find it out very simple examples. By a repetitive type of practice you can have a mastery over all examples. Thank you, stay safe and best of luck.